All right, so welcome everyone for our, I think, fourth UNR postdoc webinar. I think this has been a successful endeavor. We've seen really interesting research from a lot of UNR postdocs, and it's been kind of educational to learn about the work done by postdocs in a lot of different departments. So for this month, we welcome Dr. Kamran Binaee. He's a postdoc researcher here at UNR, and he has his PhD in imaging science from Rochester Institute of Technology. He's been formerly an intern at exciting places. He has a background in electrical engineering and software and hardware development. So really kind of, I think, a unique mix of experiences. I'm very excited about this talk. So without further ado, I will give the floor to Dr. Kamran. Thank you for being with us today, and please go ahead. Looking forward to your talk.
Thank you, Maha. Thank you so much. I guess, first of all, thanks to Maha, Zoe, Daniel, Matt, and all the Postdoc Association folks. You guys have done an impressive job. Less than a year, setting up everything from scratch. And it's just amazing watching how progress you guys have made. And thanks for the opportunity very much. So yeah, today I'm going to talk about a little bit why do we need to have large-scale data in a very general sense, and how does it help the growth and the progress in industry and also in research, and how does the visual experience project contributes to this kind of general goal. And I will talk a little bit more in detail about the major challenges that we have been facing during the past year and a half for setting up this system in order to allow us to collect such data set. And then I'll share with you our current design and current hardware and software system as an overview, and also what kind of characterizations and system studies we conducted to make sure that the quality of the data we're collecting is at the level that we are kind of satisfied with that. And then I will wrap up the last part of the presentation with the current work and current projects that are happening in the labs that I'm happy and I'm excited to be able to contribute to that work. So in a very big general sense, the big data has contributed significantly to recent progress in the field of computer vision, machine learning, and AI, which these terms sometimes can be used interchangeably, wrong or right. For instance, the current developments in Boston Dynamic robots, they can perform very, very impressive tasks that were kind of a dream 10, 15 years ago. And they are capable of performing these tasks under a wide range of variability. And just to share another example from Facebook AI, which is kind of related to what we are doing at the end goal, from the end goal perspective, is this recent success in object detection, object recognition, object tracking has been mostly driven by the availability of large data sets, large annotated data sets. Okay, so one common theme for most of these recent developments is the fact that these algorithms are trying to mimic the sort of processes that happens in the brain. And here I'm just kind of trying to show the similarity between an artificial neural network, to be more precise, a deep neural network shown in the bottom, and the way that it kind of tries to mimic the processes that happens in the brain. Okay, let's say you want to classify this image, that whether it's a dog versus cat, it passes through several layers of processes that, in fact, they are kind of inspired by the way that the brain processing layers are structured. And you have these different tiny little knobs, if you will, these mathematical weights that the goal is you are supposed to optimize them. And it turns out that they are very much inspired by the way that the brain works. So going back to the big data conversation, it all comes down to us studying the brain and knowing the brain well enough. And the question is, do we really know the brain in the way that it would work in the real world, unconstrained natural environments? I think there's a lot more work to be done here. So that's why the visual experience database is trying to understand brain mechanisms, and through collecting large data sets that has enough variability, and at the same time we want to be as close as possible to the way that the brain, so-called quote and unquote, perceives the world around it in a natural condition. Okay, so the goal of visual experience database is to create a large collection of videos, and the numbers are about more than 240 hours of daily activity, and from the perspective of the way that the brain kind of perceives the world. So the egocentric videos is where we're going to go with. And also we definitely want to include eye tracking data, being able to track the position and orientation of the head because of the synergy that is with the movements of the eye versus head. So that's a very critical part of the problem. And on top of that, we would also want to collect GPS data and some metadata about what the task is, what the participant is doing, and we're trying to be as wide as possible in terms of including a wide range of participants. And before I jump into the details, I should also say that this is a very collaborative project across 3 universities. Dr. Green from Bates College, Dr. Ballas from North Dakota University, Dr. McNeil is my postdoc advisor at UNR, and Dr. Lescourt at UNR. So it's truly a collaborative project and a long list of talented graduate and undergraduate students that we are collecting data. This is just a snippet of the current tasks and environments that we have been able to collect data on. So as you can see, indoor, outdoor, participants being active or sitting somewhere. So it's relatively very wide variability at many different levels. And this video, hopefully, these sample videos hopefully will give you some example of, for instance, me driving my bike by the San Rafael Park and collecting some data over there. So we're trying to go kind of, if you will, crazy in terms of data collection, and it's going to force us a lot of constraints. So far, we have collected 40 hours, a little more than 40 hours of data, and the rate is 50 gigabytes per hour. So it just gives you a little bit of scale and range of size of the data we're talking about here. So when we started collecting and creating this system, what major challenges were the ones that we were trying to tackle? First of all, the existing eye tracking systems, for instance, Pupil Labs, one of the most famous ones, suffer from the roll camera properties, both in terms of field of view, resolution, and also there's no known device that track the head position at the same time. All of them just track the roll video and the movement of the eyes. That's it. So that's one of the major challenges here. Also, eye tracking accuracy outdoor is a very challenging problem, which we already knew stepping into this project. Another major problem is the storage, data retrieval, and analysis, which, again, for the sake of time today, I won't be able to cover them, and I will mostly focus on the top 2. This is the world video, the world camera that we're using. So much wider field of view because there's going to be a lot of visual information available for the brain as we are navigating the world. So we're trying to capture as wide as possible. And here I'm just trying to compare this with the existing world camera from the Pupil Labs device. So let me dive in a little bit more into what kind of system characterization and what kind of device we're using. This is our current end product. As you can see, we use a FLIR camera as our world scene camera. And we're using T265 integral sense for tracking the head movements, and then the eye tracking device. And Bharath Shankar, shown here as one of our very talented graduate students, spent a lot of time designing 3D printed mounts for putting together all of these different devices and also considering the ergonomic. So the one that he's wearing here is what we call it the soft rig, the soft head-mounted device, which provides a little bit more flexibility and feels more comfortable. The other one is the hard rig, which sits on your face more snug and kind of I would say less comfortable for longer data collections beyond 30, 40 minutes. And we also use GPS IMU device here for tracking the location and also the pose of the body for future analysis. Here I'm trying to show a list of parameters and the current status of the system and what constraints we considered when we were trying to make this call and make the decision in terms of what hardware/software we're going to end up using. For the world camera, we are using a 30 frame per second, a very high resolution, again, not compared to the iPhone or existing other cameras. For head-mounted devices, this is one of the highest resolutions, 3.1 megapixels almost. We're using a very high, wide range of wide field of view lens and camera for these purposes. And also we do want to have access to very detailed properties of the camera, for instance, exposure, brightness, color qualities, so that we have freedom to set those parameters for the camera depending on what lighting condition we are collecting data under. And for the eye camera properties, we are collecting data at 120 frames per second because we want to include most of the very tiny little fast eye movements that we tend to use. And the eye resolution video is 400 by 400 pixels. What sort of studies we conducted to characterize the quality of our world video? A big problem or a big question unresolved for us was how much compression we are trying to apply to the video that we're collecting outdoor. Okay, so the question is, first of all, we do need compression. That's for sure. There's no algorithm or there's no camera that produces raw videos because the size is going to go crazy. The question is how much compression is good enough. Okay, and in order to explain that here, I just brought this figure to say that the way that the algorithm works for compressing videos, it considers a window of the previous frames and it applies certain compression algorithm based on the content that was shown in the previous frames. So if we increase this compression ratio, if we want to compress a lot, it's going to take a longer time. Therefore, the camera won't be able to write the frame at the frame rate that we want to on the, for instance, laptop's hard drive. Okay, so there needs to be some compromise happening here of how much compression and how fast we are going to compress each frame and record it into the disk. So we basically ran a simple study to change the compression properties. In this case, CRF is constant ratio factor. That when we increase that, we're applying more compression to the video. So the image is being more compressed and the size is being smaller, but at the same time, it takes more time. So it's just not going to be ideal if we apply too much of compression. And on the other side, we have these parameters for the preset, that is ultra fast, very fast, slow, and very slow. And we ended up picking this setting, which gives us slight compression on the video to decrease the size, but at the same time, the frame rate that we can write to the disk is about 75 frames per second, only for the world video. So that's how we kind of optimize and we decided what setting should be used for the compression. I talked about video image quality, right? One of the parameters that we considered was if we apply compression, how much of visual content are we going to lose? In this specific representation, I'm comparing the image quality compression versus root mean square error and universal image quality index. Meaning that using the same presentation that I showed before, with increasing the compression ratio, we are losing the quality of the image. Okay, and in this case, we picked the ultra fast setting here shown in orange, which gives us an almost equal visually non-noticeable difference when we are recording these videos. And similarly here with the RMSE plot, it gives us about the same error as the most ideal, least compressed setting. So we're kind of all decided and set in terms of what parameters are optimal for our cases and for our purposes. In terms of gaze accuracy, on the right side here, you can see the, actually this was supposed to be a GIF, but it's not moving anyway. So the participant is holding the reference pattern and looking at it, fixating at it. And you can see the gaze is shown as a green circle here. During the gaze calibration, the so-called gaze calibration procedure, okay? And then the pattern moves in the field of view, and the idea is to cover as much as we can in the field of view. What we end up having from this calibration procedure is a mapping or a coverage region of how accurately we are tracking the gaze, okay? So the red circles here are showing where the marker was detected in the world view. And the crosses, the blue crosses, are where the gaze was calibrated or estimated. So this is called kind of a gaze accuracy heat map, right? And ideally across the field of view, we want to be this value about 2 degrees, below 2 degrees. The lower the better. And this is a good example of one participant. And as you can see, we're covering a very wide range of field of view, which is not typical for the previously eye tracking applications, plus minus 4 degrees horizontally and plus minus 10, 15 degrees vertically. Question is this the case for all of the data we're collecting right now? And I guess you can say that it's not the case at all, right? So this is the same plot for 8 other participants, 8 other sessions that was collected indoor and outdoor. For some of them, things look okay and good, but for a portion of their field of view, we are not getting a good gaze tracking values, gaze tracking accuracy is shown here in red. And for some other sessions, it's actually totally wrong, and the accuracy is very, very poor for gaze tracking. And the reason for that, one of the reasons for that is if we are trying to perform gaze tracking indoor, because of the fact that the eye camera uses IR light, and indoor, there's not a lot of IR light in an indoor setting, things are okay and things work perfectly fine. But as soon as we go outdoor without any cover, because of the abundance of IR light, the eye images look like something like this, which is extremely washed out, and it's very hard for the people tracking algorithm to work. So in order to tackle also this problem, what we ended up doing was we said, okay, we have these eye camera parameters, for instance, brightness, gamma, and sharpness, which will determine how bright or how dark or how much contrast you can include in your eye image. Let's play with these cameras systematically and find what setting is the best. To be more specific, under outdoor condition, under shade condition, and under indoor conditions, right? So for each of these lighting environments, what I'm showing here is we are changing the parameters, for instance, brightness, 4 different values, and also the gamma, again, 4 different values. And the goal here was to find what is the best camera setting for that specific lighting outdoor condition. And what we ended up saying was, okay, for instance, for outdoor, it seems like this one provides us the most accurate people tracking value. And similar for other conditions, we ended up suggesting a valid range for eye camera settings in order to provide us with decent gaze tracking accuracy. And these are just kind of like a very brief overview of what type of problem that we have been trying to solve. And as I'm sure you would guess, things go on and the problems and issues come up. What are the types of problems that we are working right now, and what are the current ongoing projects in different labs that I'm lucky to work with them? So one of the as I mentioned earlier, most of these algorithms, these people tracking algorithms, are trained under indoor lighting conditions of the eye images, and that's how they are capable of tracking the eye successfully. So I developed this tool for annotating the eye images. So as you can see, are very awesome undergraduate and graduate students are helping us to label these different regions of the eye. For instance, the iris is now being labeled. Okay, when they are done, now we know the ground truth for that specific image, and we do the same thing for about 400, 500 images in our data set. So because we have collected the data and we have access to the raw information in every image, we can create the ground truth, and we can retrain these networks, retrain these people tracking networks under the new lighting conditions, for instance, the outdoors, so that we can improve the eye tracking accuracy. Another line of work that is being conducted in Self-Motion Lab with graduate students Savi and Brian and Christian is to develop some kind of visualization tool where we now show the synergistic movement of the head and the eye. Okay, so for us, this is a tool developed in Python and Unity. And as we were getting closer to Halloween, I guess this was a good choice by Savi by using the imagery here. So the goal here is to show the different streams of data that we're collecting, right? So part of the problem is vetting the data, making sure the data is valid, and each of these streams are doing what they're supposed to do. So for instance, the top panel is showing the rotation of the head, as the participant is doing this kind of head movement while fixated at the center. And the bottom row is showing the gaze values, that how the gaze is moving. So ideally, if this is the case, this is referred as to VOR head movement or vestibular ocular reflex. So these sinusoidal data coming from the head and eye should be kind of counterbalancing and canceling each other if everything is working perfectly fine. So it's kind of a test for us to visually check whether the streams of the data are being recorded correctly or not. And then, as I mentioned earlier, while we are trying to retrain these networks, now we are going to hopefully improve the quality of the gaze tracking for output. What is happening in this presentation is you see the input video here, the contrast enhanced video on the second column, and then these are the regions detected by the deep pupil tracking algorithm. The way that this algorithm works is it receives the eye image and it produces the map that where the pupil, where the iris, and where the sclera was detected in the image. Based on that, we are basically using simple pupil fit algorithms to fit the pupil. So as you can see, it's not ideal yet. So it's an ongoing problem. At some point, the algorithm doesn't do a good job finding the accurate position of the pupil, which is going to affect the gaze tracking accuracy, right? And things get worse if we go outdoor, as I pointed out to this point earlier, right? So now we have the reflection of the world on the iris as the person is walking in the world, and that already creates a lot of noise and a lot of problem for the people tracking algorithms. So things gets very worse and very, very kind of out of control if we do not take into account the range of images that we collect outdoor. That's exactly one of the things that we're trying to tackle right now by modifying these pupil tracking algorithms. Another, I guess this is my last slide for today, where we are now trying to study the effect of slippage. So this device is sitting on the participant's face, and at the beginning of the data collection, we have a good accuracy, everything looks okay. But as they are walking, as they are being active, the device shifts slightly on their face, and this causes gaze tracking error, right? As I tried to mention earlier, one of the goals is to not constrain the participant at all, as much as we can, obviously, and let them do whatever activity they've been doing. So what's the effect of slippage on gaze tracking accuracy? That's what we have been studying in Self-Motion Lab, again, with collaboration with Bharat Shankar, Brian Jeckley, and also Dr. McNeil as advising the whole effort here. So basically what we are doing here is we're walking under 3 different speeds. And after each session of walking, which is about 2.5 minutes, we validate by presenting a known pattern on the display. And we just ask the participant to keep looking at them. So we have a grid of 3 by 5, 15 points that we know where the target is, and we are collecting gaze tracking data so we can figure out whether the gaze tracking was inaccurate and how much it was. What we end up saying here, again, these are very fresh preliminary results as we are going forward, is this kind of visualization. The initial validation after walking slowly, after walking with medium speed, and after walking fast. And red, again, is the target, and crosses shown in gray are the estimated gaze across the screen in front of the target, right? So we can start seeing the slippage happening clearly here, right? So the gaze versus target is kind of being a little shifted away from each other as the data collection proceeded and as the device shifted slightly on their face. We are hoping to be able to use this kind of offset to correct for real case scenarios where participants are outdoor and they're being active, so that we make sure that the quality of the gaze tracking remains the same. So I hope, although this was very compact and quick talk, I hope that I was able to share with you our efforts in terms of creating this data set and why this is important in terms of allowing us to study vision in more naturalistic setups. And also, I shared with you some of the current challenges that we have and also what problems that we were able to tackle so far. And in the future, we're trying to basically expand upon the data collection efforts, wider range of participants, even outdoor university, and being able to work more on the data storage and data that is being uploaded to the cloud. So yeah, and then toward the end, I just want to thank my advisor, Dr. McNeilage, a talented group of students here at UNR, and other PIs from other institutes, Dr. Green, Dr. Ballison, and Dr. Lasquar, and obviously the funding agency, NSF EBSCOR grant, and again, you guys at UNR Postdoctoral Association for the opportunity. We'd be happy to take any questions.
Wonderful. Thank you again, Dr. Binaee, for the very interesting talk.